Hi guys, thanks for tuning in. This is part two of my lecture about surface integrals. Yesterday we really emphasized the net flow of a vector field across a piece of surface. In this case, we are going to let go of the entire vector field thing, and instead we are going to take a parameterization for a surface, and we're just going to find its surface area, no vector fields to worry about at all. Now what you'll notice here is f of xy equals sine of y cosine of x over 2. That's not yet a parameterization. But if you ever get an f of xy, you can parameterize your surface for free. All you do is, this will work every time, your x of uv, make that u, your y of uv, make that v, and then your z of uv, just take your function f, and instead of plugging in x's and y's, plug in u's and v's, and that's going to give you your z of uv. And that's a parameterization that we get for free for this piece of surface here. And the reason that we care about this is that we know that if we can parameterize a region, we could probably integrate over it. So what we're going to do is we're going to take this parameterization, try to come up with some sort of surface area conversion factor, and then we have an integral we can compute with nice limits of integration. 0 to 2 pi for v, 0 to 4 for 4. We're going to need some surface area conversion factor that allows us to go from x, y, z space to an integral in uv space. But this will be an integral that's pretty easy to compute. And now let's kind of see why we would need a surface area conversion factor to do these problems. At its core, it's basically the same as why we needed an area conversion factor in previous chapters. Our mapping is not area preserving, or in this case, surface area preserving. In UV space, we have a rectangle. And in XYZ space, we have this wavy piece of surface right here. And what you guys can see is a point UV in our two-dimensional space maps over to a point on our surface, uv sine v cosine u over 2. Well, there's stretching and compressing that happens in the course of this mapping. So if you take a rectangle of fixed size in uv space and map that over to xyz space, depending on where that is happening, there's a different amount of stretching and compressing. And because of those differing amounts of stretching and compressing, we need a surface area conversion factor. Now the good news is the machinery to come up with the formula for the surface area conversion factor is not really that different than what we saw in the purely two-dimensional case. The formula looks different in the end, but the process for getting it was not really that different. All we need to do is think about how a small UV rectangle maps into XYZ space, and we can try to estimate that surface area using a parallelogram, just like we did in the past, and it works out pretty nicely. So I want you guys to imagine a tiny little rectangle in the UV plane. There it is. It's du on one side, dv on the other side. And that tiny little rectangle maps to a tiny little piece of surface. And what you guys will notice is that the amount of area for the rectangle and the amount of area for the surface will vary depending on where you are on that surface, right? But we could approximate this surface area in XYZ space using a tiny little parallelogram. And it's the same trick as before. We use two little tangent vectors there. We get those tangent vectors by taking the partial derivatives of our parameterization with respect to u and with respect to v. Those are our two little tangent vectors. Then use those two little tangent vectors to find the area of a little parallelogram. And you guys already know how to do that. The magnitude of the cross product of those two vectors is going to be the area of that parallelogram. And it turns out that that is also going to be our area conversion factor. So that formula that we learned right at the beginning of the year, that the magnitude of the cross product is the area of the parallelogram that it outlines, that turns out to be a super useful formula because it keeps coming up over and over and over again. Now, the interesting thing that we didn't really talk about in a previous chapter, because we weren't talking about three-dimensional space, but now that we're in three-dimensional space, this cross product here takes on some additional meaning, right? Because the cross product of two vectors gives you a vector that's perpendicular to both of them. We're going to get a normal vector, right? And so, interestingly enough, the area of this parallelogram, here, and the length of this vector are the same, right? Because the magnitude of that cross product is going to be the area of that parallelogram, but the magnitude of that cross product is also going to be the length of this normal vector. So kind of a strange thing going on here. The length of that normal vector is representative of the size of the surface area conversion factor at a particular point, which is kind of cool. If you guys are interested in exploring that idea, I do have a Mathematica demo that you can download from Schoology, and there's a slider that you can drag, and you can see as the normal vector is moving over this surface, the normal vector is changing size, and that changing of the size of that normal vector represents the surface area conversion factor getting larger or smaller at particular points. It's kind of a measure of the curvature of the surface at a particular point as well. Anyway, so I do have some bad news. The surface area conversion factor's formula is very long because it's the magnitude of the cross product of two vectors. On a quiz, you would want to be able to kind of reproduce that formula and then use that formula for some computations. Now, the good news is, even though the formula is really long and it looks complicated, the individual pieces are all things I know you guys are very good at, right? So the first vector in this cross product is just a partial derivative of x of uv, y of uv, z of uv with respect to u. Well, you guys are good at taking partial derivatives, no big deal there. Same thing for that second vector. Take your parameterization, take your x of uv, y of uv, z of uv, take its partial derivative with respect to v. Again, a skill that you guys are very good at. Then you take the cross product of those two vectors. Again, you guys have a lot of practice with that. And then finally take the magnitude of that cross product, because we do need a scalar quantity if we're going to integrate. And the magnitude of that cross product will be your surface area conversion factor. When you're working in Mathematica, luckily the computer is going to do a lot of that number crunching for you, but you should expect that, on a quiz or on the final exam for the course, it is reasonable to have to compute a couple of these surface area conversion factors and do some integrating with them. All right, so here's just a little summary of everything I just showed you guys. It is possible to squish down this formula just a tiny bit. If you think of your parameterization, your mapping, as a transformation, your x of uv, y of uv, z of uv can be thought of as a t of uv, a transformation. And then you could kind of squish down these formulas a little bit. And, these are all equivalent notations. I don't really mind which one you want to work with. They all mean the same thing. Of course, on a quiz, if you wanted to save space, that the middle one involves writing the fewest number of characters, if that's of interest to you. But it's also the one it's least useful to actually compute with. The first really long formula is nice because you can actually crunch numbers with it. Anyway, now that we have a definition of the surface area conversion factor, we can compute integrals for surface area. We can compute a surface integral for computing the surface area of a piece of surface. It's just said the word surface a lot of times. Anyway, you'll notice that I did not put absolute value bars right there. That's because the magnitude of a vector is the square root of the dot product of the vector with itself, right? And so when we take the magnitude of the cross product, we are going to take the square root of the dot product of that normal vector with itself. When we take a square root, that's by necessity going to be positive, right? So you don't need absolute value bars there. And then everything else is pretty straightforward. What's nice is, look at these limits of integration. If you have a nice parameterization for your piece of surface where these are integers, computing that surface area, at least on the limits of integration end of things, will not be so bad. This is the same material right here, so don't worry about that so much. It's just, I put the transformation notation there. And then I should mention that there is a very close relationship between last year's arc length formula and this year's surface area formula. They're the same formula, just in higher dimensions, right? Add an extra integral symbol, and then the surface area conversion factor, and this term that you guys had underneath or inside of your integrand, this integrand, they're serving an equivalent purpose. And actually, if you play with the symbols for a little while, you'll actually notice that they come from the same mathematics as well. And if you have some extra time, you try to find that connection between the surface area conversion factor and that square root that you had in your arc length formula when you were in Calc BC. All right, so let's crunch some numbers. Let's do a problem. So first thing you have to do is, if you have a surface, you got to parameterize it. You need a surface to be written parametrically for this to work right. Now your surface better have bounds, because the bounds for that piece of surface will also be your limits of integration for your integral. Now, is it possible to compute this particular surface area conversion factor by hand? Yes, but you probably don't want to. And so I actually ran that through the computer. If you were going to see something on a quiz, it probably wouldn't be quite as ugly as this, right? Possible, but it seems unlikely. Anyway, also I don't want to take the double integral of an expression that has the square root of blah, 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 blah as its integrand. So I also don't want to do that surface integral by hand. So I ran it through Mathematica. That's what's nice about taking a course like this, because you can do problems in Mathematica that you would have never been able to do by hand. Now, is it possible to finagle these so that you could find a surface integral for surface area that you can do as a hand calculation? For sure, and you'll see that on the quiz. But on the teacher/professor end of things, you have to work pretty hard to make a problem that's actually doable without the aid of a technology. So, cool application of this material is if you pretend that this piece of surface is a really thin piece of metal, like it has a thickness, but its thickness is inconsequential because it's so thin. And if you pretend that the surface is made of a mixture of different metals that have varying densities, we could find the mass of that piece of surface as long as we put that density function into our surface integral. So we are still going to use a surface area conversion factor, but we're going to throw in an integrand for density, and you guys know what happens when you accumulate density over a region. You get the mass of that region. So in this case, if we accumulate density over this surface, we get the mass of the surface. Now, this is obviously idealized, because in the real world, a piece of sheet metal is not infinitely thin, and therefore, it's not going to have any, in the real world, this thing will have mass because it'll have some thickness to it. In this idealized version, you wouldn't expect it to have any mass because it's infinitely thin. But you have to suspend your disbelief here and just remember that we're talking about an idealized situation where we are pretending that the thickness of this thing doesn't really matter so much. Anyway, so we could say that that this piece of sheet metal has a mass of 174.221 grams. Pretty sure you're going to see a try-it problem that's just like this. So you'll get to practice it in Mathematica. And then, here's my summary. So when you are computing surface integrals, you're going to need to put in your density function, a surface area conversion factor, and then you're going to integrate with respect to whatever your variables are that you came up with for your parameterization. Now, the reason I like this mass way of explaining surface integrals is I feel like that's something everybody can kind of sink their teeth into, right? If you think of this as a density function, and if you think of this overall calculation giving you mass, that's not too hard to wrap your mind around, because we already know that accumulating density over a region is going to give you the mass of that region. And so that's pretty natural based on our background in this course. That being said, some of you guys are going to go on and take some pretty advanced physics courses, and you see surface integrals all the time in those higher level physics courses. Well, I don't want you guys to get intimidated by those surface integrals because at the end of the day, they're going to be just like the computations we're doing here. I don't care if we change out density for charge density, and I don't care if we are computing mass or if we're looking at the total charge over a piece of sheet metal. The computations you're doing are going to be the same. So when you get to those harder physics courses that you might be taking in the future, don't get scared away by this whole surface integral thing. We're just accumulating a function over a surface, and whatever we're accumulating is going to depend on the context we're working in, but it's never going to be that different than the idea of density to accumulate mass. All right, and then finally I have one just cool thing to show you at the end. So I'm going to stick with the same piece of surface here, still a wavy piece of surface. Actually, did I change the, yeah, it's the same surface, sorry. There we go, that's what I was looking for. So I did not change the surface. You can see the equation here stayed the same. But what I am throwing in is now pretend we have this piece of metallic sheet metal, and we have maybe one of those laser machines like they might have down at the Applied Tech department. We're going to use that laser machine to laser out, to cut out an elliptical piece of our surface. We actually know enough mathematics to find the surface area of that piece of surface that we're going to laser out. Now, we are given at the beginning of the problem the parameterization for the path that the laser is going to follow. So it is a perfectly elliptical region that we're going to shave out, or that we're going to cut out of our piece of surface. And we do need to take our parameterization and actually fill in the ellipse. So the given parameterization at the beginning of the problem is for the outer boundary of the ellipse. We do need to fill it in. And all I did was throw in an extra parameter there. S is what I called it in this case, and I let S go from 0 to 1, and that will fill in the region. Now we need to map that elliptical region onto our piece of surface, which really just means plugging stuff in, right? So look what we have going on down here. If we say that u of st is equal to 2s cosine t, by the way, that's from right up here, and if we say that v of st is 3s sine t, by the way, that's from right up here, we could throw that into our x of uv, y of uv, z of uv. Now it looks ugly, but it's not as bad as it necessarily looks. We have x of u of st, v of st, y of u of st, v of st, and z of u of st, v of st. It's just two changes of variables. The original change of variables for the parameterization for our surface, and the second change of variables for our parameterization for our ellipse, and we just plugged one into the other. And this just shows you the same thing I was just talking about, the second change of variables. So if we want to compute the surface area of this lasered out elliptical piece of surface, we just have to throw in an area conversion factor to adjust for our second change of variables. So we have our original surface area conversion factor, which we already previously computed. Now, the original surface area conversion factor was a function of u and v, but now we are switching from a du dv integral to a ds dt integral. So I need to change out the u and the v for u of st and v of st, but you can't just arbitrarily change your variables in an integral. You have to adjust for that change in coordinates, right? And so we need an area conversion factor that lets us go from a uv integral to an st integral. And it's the same area conversion factor that you guys are already familiar with for an ellipse. So not really that big of a deal there. So let's crunch some numbers here. By the way, this little progression hopefully helps you imagine what's going on. What's nice about the integral that you saw on the previous slide right here in the lower right-hand corner, what's nice about that really long expression is it might look really ugly, but at the end of the day, this integral in ST space is integrating over an ST rectangle. Look at our limits of integration. S goes from 0 to 1, t goes from 0 to 2 pi. So will this integrand be kind of ugly and complicated? Sure, but our limits of integration are very, very nice. We want to integrate over an ST rectangle. By the way, that came from our UV ellipse that we parameterized, which that UV ellipse, by the way, came from a piece of surface on that wavy piece of sheet metal. So that's how that all ties together. So we're basically plugging one change of variables into another, which is why we have both a surface area conversion factor and a regular area conversion factor. So the area conversion factor, you don't need a computer to do that. You guys know how to take a change of variables, in this case 2s cosine t and 3s sine t, and get your area conversion factor. It's the same thing you guys are familiar with from previous chapters. I got 6s there. The surface area conversion factor we already found in a previous problem, so we're going to reuse that. Now, I know it's the absolute value of the area conversion factor. Over our bounds, 6s will never go negative, so you actually don't need those absolute value bars. But anyway, we let Mathematica do the rest of the hard work. And the surface area of that elliptical cutout piece of wavy surface is about 22.0667 units, whatever those units might be. All right, finally, and what I'd like to close with, yesterday and today we learned two different kinds of surface integrals. These are often referred to as vector surface integrals versus scalar surface integrals. It's a little bit of a misnomer because all integrals that we know are integrated, we're integrating scalar quantities. But what that's referring to is the fact that yesterday's work was starting with a vector field, right? We had the net flow of a vector field across some surface. And so that's the sense in which this is a vector surface integral. Now, you are going to take that vector field, and when you take the dot product with your normal vectors, you do end up getting, a scalar quantity there. But it's a vector surface integral in the sense that the formula involves a vector field. Today's a little bit different. Everything was scalar, right? So we, in this case, just worry about our surface, right? We don't have a vector field. There's no flow across. We just need a surface area conversion factor so that we can integrate these quantities using a nice integral that has hopefully integer bounds for our limits of integration. All right, guys, I hope you enjoyed today's video, and that's the last of these lectures for this chapter. So good luck on your tryouts. Good luck reading the basics and tutorials.